Afternoon, everyone. I think we're going to get started with the next presentation. My name is Justin Jang. I'm a data scientist at AWS. I work in the Generative AI Innovation Center, where my team in particular helps customers build proof of concepts for Gen AI and large language model pipelines. Today, I'm going to sort of share with you all some of the best practices we've seen in building text-to-query language pipelines. So if you've ever heard of sort of text-to-SQL, where you input a natural language query and out you get SQL or SQL, we've worked on probably 4 or 5 different use cases to date across national security customers as well as FedCiv on some of these similar problems. So I'm going to share some best practices that we've come up with in building some of these pipelines. I'm going to feel free to interrupt at any point if you have questions. I'd like to make this a bit more conversational than just me talking at you. So today we're going to sort of briefly talk about the problem space. What is text-to-query language? What are some of the challenges in building some of these pipelines? We'll talk about best practices that we've seen in making sure that these pipelines are sort of runnable in production, and they're actually effective, they're querying the right data. And then I'll try to do a system demo of a particular query language, CQL, which stands for Common Query Language. It's a less used query language than SQL, but it's a use case that we worked on for a national security customer, and we can talk about it sort of at a high level. And then finally, the sort of what do you do after you build an effective text-to-query language pipeline? We'll go beyond that and kind of talk about more sort of agentic systems and how do you wrap these text-to-SQL pipelines in sort of a broader system. So I'm just going to talk about the problem overview for just a brief moment to get everyone oriented. So in terms of converting natural language to a database query. So on the far left is the user query. What are the names and budgets of departments with average instructor salaries greater than the overall average? That's something that a data analyst or a user might want to query. In this day and age, maybe like in the last 2 to 3 years, LLMs have been very heavily utilized to actually convert these queries or natural language questions into actual runnable queries. Typically, they have access to the database schema. Is my mouse? I think the input. Sorry, where am I doing that? Oh, the Wi-Fi dropped.
Yeah. It says no connectivity on your screen in front of you. Actually, you got it here. It's just not connecting to that. Are you wirelessly connected?
I'm on the Wi-Fi.
Yeah, you're seeing it. Oh. No, forget it, and let's rejoin it with a new password.
It says it's connected now.
Is it showing up there? Forget that network and rejoin it. Give you a new code for it.
I have to go to Wi-Fi settings.
Sorry.
Forget this network.
And then let's rejoin it with a new code.
It's the first one.
Yeah.
Huh. Still.
I have to remember.
Now it's joining the other one. We don't need this
No.
one. Thing is, I think it still remembers the password.
Yeah, it might from your computer settings. We're not going to mess with that. showing 5 bar, full bars.
But isn't this HDMI up here? Why do I need the Wi-Fi?
Are you reading this off Wi-Fi or?
No.
So that's why. So I can't tell for what.
Oh wait, you know what? Let me save this locally. It might be, that might be the exact problem.
Is it you're not running it off your desktop?
Yeah,
Okay,
that's
okay.
interesting. Okay, gotcha. Let me
Maybe
see.
that will work. Sorry, just a couple more
1
seconds.
second.
It's showing up now.
Oh, that's the other one.
Yeah. Just so we have no problem.
Is this one showing? Okay, sorry about that. Yeah.
All right.
That was running off like a shared drive, which required Wi-Fi. Okay, so just to step back, when we think about taking natural language and generating a database query, over the last couple of years, large language models have been heavily utilized to generate the query for you. So again, the example is what are the names and budgets of departments with average instructor salary greater than the overall average. Typically, that's something you could just give to an LLM, and the LLM would have some knowledge of the database schema that you have access to. It generates the query, it runs it against the database, and it gives you sort of a table of the results. So that's at a high level the problem we're looking at today. So there are a couple sort of issues with this process where you can very easily demo toy examples, but when you move to production, it becomes kind of tricky. So the overall problem, just at a higher level, is that users simply don't know what data exists oftentimes. They don't understand if there are tables, what the tables actually tell you. And then there's also a technical bar. So if you're not like a seasoned data analyst, you might not have sort of an understanding of how to construct advanced queries. You also might be working with less common query languages, which is very actually common in sort of the public sector space. So there is sort of a common query language, which is CQL, and not to be confused with SQL. That's something we've worked on for public sector customers. And another sort of use case that we recently took on was how do you convert natural language to an open search Lucene query? And that, again, has very specific syntax that most people don't really know how to construct by hand. So we're going to go through some of the lessons learned in building some of these today. So just to revisit this example, again, what are the names and budgets? The syntax on the right is actually very simple looking, right? There's like a select statement, there's a from statement, there's some sort of join because the data live in 2 different tables, and some sort of additional operators like taking the average of the salary column and comparing it to the overall average. So syntax-wise, it's actually fairly easy to construct. You don't even need an LLM to do this. You could probably just build business rules to construct the query. But there's more to it, right? We need context about what the data is, what tables have information about department names and instructor budgets, what are the exact column type names, and what are the actual attributes? Are they string, float, categorical, et cetera? And then there's also questions about, well, you can write the query in n number of different ways. Is it properly optimized to run quickly? And there's all these other considerations that make this task actually pretty difficult. So when we think about sort of building these systems, text-to-query language, there is a design space that we have to think about. So starting from the left, there is the user query, and all the way on the right is sort of the answer. And the answer might not be just the rows that you get back from the database. It might actually be an LLM summarizing the results of the database query. But to think about some of the intermediate steps, there are actually pieces that make this whole system a bit more effective. So the first thing after the user query on the left is query disambiguation. So for example, if you were to sort of search a query that had maybe the location name Paris in it, does that Paris refer to Paris, France, or does it refer to Paris Hilton, the celebrity? There are all these different terms in a user's query that is ambiguous, that needs to be resolved. A couple things we're going to talk about today is, one, how do we actually get the right categorical values? We've actually done some work around ontology resolution that takes an ambiguous term and resolves it to a standard sort of ontology or a knowledge base with standardized terms that exist in databases. So we'll talk about that a little bit. In the sort of public sector space, a lot of queries involve spatial elements. So find me all airplanes around or flying over the continental US, right? And so you somehow need some notion of geography and spatial coordinates. So the US needs to be resolved to United States, and then United States needs to somehow be converted to coordinates. So we'll talk about some methods for location resolution, which actually help you build more sort of feature-rich pipelines. The next step is schema linking. So schema linking is a fairly standard thing that you want to have in your pipelines. They essentially tell the large language model what are the field names in our databases, what do the data look like, what are the data types. We want to have it choose the correct table within your database. So we'll talk about some sort of heuristics for doing schema linking. And then finally, in the center, we have the LLM-based query formulation. So if you've been working on this problem, you'll know there are a couple different techniques to have the LLM actually generate valid queries. There are some sort of traditional techniques like giving example SQL queries and the actual prompt. That's few-shot prompting. For more complex queries that involve multi-part or subqueries, you might want to break the problem down. And that's what I call sort of disaggregation. And we'll see an example of that in just a second. There are also RAG-based approaches, which have become pretty common for retrieving queries that have been run in the past by users. So you can actually maybe create sort of a vector database of past queries run by analysts or whoever's hitting your data. And you want to first semantically find a similar query that was run in the past and potentially use the actual query language associated with that natural language query as an example to give the LLM. So that's sort of been more common. And then sort of more advanced techniques is things like structured output. So if you're working with like a non-standard query language, text-to-Lucene, for example, that particular use case requires you input or submitting a valid sort of JSON structure with the search terms. Structured output is a way you can leverage LLMs to generate actual JSON with valid inputs for that particular query language. And then if you have a lot of historical examples of valid queries, you could actually fine-tune the model, but that's a bit more expensive to do. Finally, you hit the database query. You can introduce human-in-the-loop elements to these systems. So human-in-the-loop just simply means let's interrupt the flow of the pipeline and ask the user if the generated query is something they will actually want to run before they run it. So human-in-the-loop, we've worked into various use cases around the government, and it's been an effective sort of intermediate step to give users a bit more control over the process. Once the database is actually queried with the LLM-generated query, sometimes the database can throw errors, and those errors are extremely useful in helping the LLM correct its malformed query. So error correction is something that you should almost always include in these pipelines. Typically, it's like an exception that gets thrown at execution time, and you can take the error code and feed that back into a previous step in your pipeline. Result post-processing. So as I mentioned earlier, sometimes it's not adequate to give the user just the results of the query. You want the LLM to summarize it. You maybe want them to run another query and combine those results in sort of a post-processing step. One of the POCs we ran with a national security agency required the use of various tools after the database query to actually make more sense of the raw result there. And we'll show an example of that as well. Okay, pipeline best practices. So now I'm kind of going to step through some of these pieces that we discussed in this sort of design space flowchart here. The first thing being query disambiguation, right? So how does the large language model know the precise variable to query? One of the things we've worked on is the idea of ontology resolution. So often governments, public sector agencies have data, and they have sort of a knowledge base about what's in that data, what are the relationships in sort of a hierarchy. One thing we've integrated into a pipeline was the idea of an ontology resolution step. And in this step, what we do is, let's say a user is searching for all submarines within a specific sort of AOR operating environment. And in the database, there might not actually be the term submarine under vehicle type, and we need to use some external knowledge base to disambiguate the term submarine. So what we do here is we actually take the ontology, which is essentially a JSON or a tree-based structure of the hierarchy of vehicle types and sub-vehicle types, and we have the LLM look at that whole ontology and choose the term that most precisely matches the term submarine. And we have it also traverse the submarine tree to include all terms that relate to submarine. So in the final query, we're actually going to have the LLM choose things like U-boat or like submarine type B. All those terms get used in the final query when we use this sort of ontology resolution step. In terms of how we resolve specific locations within the text, so again, an example could be, find me all flights flying over the continental US. US has to be resolved to United States, and United States has to be translated into some sort of spatial context. A couple things you can do. Geocoding is a common practice for this, where you take sort of a location-based text and you map it to coordinates. There are a number of different services for that. AWS has location services. You can use sort of open source services like OpenStreetMaps, Nominatum. And one other thing you can do is simply have a database of location names and polygons that you can sort of look up in a RAG-based approach. One of the examples that I will show in just a second is sort of that RAG-based approach on polygons. In this diagram here, you can see I have sort of a column of both country and ocean names, and then another column of like the geometries, which were pulled from open source. And one step in your pipeline could have an LLM or a traditional NLP model extract all the locations from your query and have it do a vector lookup and replace the location name with the actual geometry in your query. So here's an example from a use case that involves text to generating common query language. CQL is sort of like the where statement or the where clause in SQL. It's sort of just a shorter sort of version, and it has its own syntax. On the left, I'm using the Claude Haiku model, which is sort of one of the most powerful frontier models out there right now. And the user query is filter for all vessels in the South China and East China seas. And the final query sort of is able to generate this intersects clause, which includes the geometry field as well as the polygons of the correct locations. I wanted to see if more powerful models could sort of extrapolate, just given sort of a basic geometry. And so on the right-hand side, I'm using Claude Sonnet 3.5, which is arguably one of the best models out there right now. And the original user query is filter for all vessels 5 nautical miles off the west coast of the US. And it goes through that pipeline, and it tries to do its best with like grabbing the west coast coordinates and adjusting for it. So it's not quite there yet. Some of these models are not quite spatially aware just yet. There are probably some optimizations you can do to have it generate sort of a better sort of fidelity polygon in some of these spatial queries. But something I just thought was interesting to share. Okay, so now going back to sort of the left side of the pipeline, there is the idea of schema linking or contextualizing your data. So oftentimes when you start on a project like this, most of your data doesn't have good schema. You don't have good descriptions about your tables or your databases. And so you need sort of a way to fix this cold start problem of giving sort of context to your data. We worked on a use case with a financial regulator where they had hundreds and thousands of tables, and they didn't have great schema. They didn't have great descriptions of what the data looked like. And so our team built sort of a pipeline that sort of uses an LLM to look at some of the schema that is available and have it generate descriptions of the tables. And we also were able to do what we call column analysis, where we actually ran some simple queries for the tables and generated more metadata or enriched metadata for the tables. So things like, what are the most common strings in this column? What are the min and max of this numerical value, sort of the distribution and that sort of thing. And we took all that enhanced metadata and provided it to the LLM downstream when it formulated its queries, and saw a huge lift in text-to-query accuracy. So this was sort of like a cold start problem where we had all this data, it wasn't good, and we actually used an LLM generative framework to give more context to the data. So that's one thing you can do at the beginning of projects like this. So I mentioned large language model best practices. At the generative piece, at the center of your pipeline, what are some things you can do to improve the generation outside of all those pre-processing steps? Again, relevant examples at inference time, so include actual sample queries that your customers or the users are interested in. Retrieval, augmented generation. Again, you're keeping track of user queries from the past, and you're feeding the model sort of a similar query that has been asked in the past to supplement its generation. Fine-tuning the model, this is a bit more expensive. We haven't really seen a lot of use cases that leverage fine-tuning, but the idea is you have sort of an instruct data set of natural language queries and equivalent query languages, and you just actually fine-tune the model to be able to do it without any sort of additional context. Passing exceptions back to the LLM, again, we have this in all of the pipelines that we built for customers. If your SQL database throws an exception, that exception usually contains useful information on why the query failed. So the LLM can take that piece of information and retry generating the query. And then, for most of these use cases, we've stuck to sort of state-of-the-art frontier models, so your GPTs, your Claudes. Sometimes you may be faced with the constraint of having to use a much smaller model because you don't have access to compute. Sort of in the use cases I've worked with, what we were GPU constrained, the Mistral model family seems to be sort of the best sort of trade-off between size and accuracy. Mistral models are generally favorable licenses. They have a bunch of Apache 2.0 sort of models. They don't require lots of hardware, and they can do some nice things like structured output and tool use, which makes them good for smaller use cases there. So kind of shared some of the best practices in doing that. I'm going to walk through sort of an end-to-end example of how we put this together for the CQL language, which again is common query language. It's really not so common. Most people aren't using this. But typically, this is used to query sort of like geospatial data because it's pretty strong in querying with geospatial operators. So here's the CQL at a high level. As I mentioned earlier, CQL is sort of like the where clause of SQL. And what it involves is generating Boolean statements or predicates that evaluate to true or false. And there's typically 3 types of CQL. So a typical comparison CQL, which is like 8. I know it's hard to see, but examples are like age greater or equal than 18, name equals John, price less than 100. So these are like typical where clauses of SQL. Again, very simple syntax. There are temporal predicates in the CQL language, and this all this involves is using a couple different literals like before or during, along with date and time strings. And then spatial predicates in the CQL language involve things like intersects, disjoint, contains, and the idea is you pass in sort of a spatial geometry and you have those operators operate on those geometries. So for this particular problem, there pretty much aren't a lot of like examples out there to fine tune or do RAG on. And for this particular problem, I use the technique of disaggregating the query to have the LLM generate one of these three different types of predicates, and then combine them in a sort of post-processing step at the end for more sort of involved queries. So I'm going to first describe the architecture of the text-to-CQL problem. So before I actually talk about the diagram a bit, here's an example of a multi-part query. And the user query here is flights arriving on May 19th, 2023, with a cabin pressure greater than 14 psi. And the first thing that the sort of pipeline resolves to is the schema name. And in this case, it's the aircraft schema. For this particular demo, I had like aircraft and ocean vessels. So this is sort of a LLM that looks at the various table descriptions and chooses which table to route to in the pipeline. So in this case, the LLM has chosen aircraft. I then ask it to disaggregate the original query into separate standalone simple queries. This helps you sort of debug the whole process better, and it kind of makes the LLM's jobs a lot simpler in just having to generate single simple queries. So in this case, the original query disaggregates to flights arriving on May 19th and flights with a cabin pressure greater than 14 psi. In step 3, we're generating these queries sort of independently. And as I mentioned on the previous slide, we're having the LLM decide whether or not that individual subquery is a comparison type, a temporal, or spatial. It then uses all this context in the prompt to generate the simple query. So in this case, the first subquery of flights arriving, it uses the correct SAT column, which is scheduled arrival time during, which is the literal in the sort of temporal operators, and then the date time range. And then for the cabin pressure subquery, it's correctly choosing this cabin underscore PSI column, which is fed into the prompt. And it's generating the simple comparison predicate of greater than 14. And then in the final query step, we're basically just mashing those two generated CQL subqueries together into a final SAT during this and cabin PSI greater than 14. So this is kind of a general flow for how you can really take kind of more complex queries and sort of build them up from simple building blocks. Again, it's sort of a bit more transparent. There is some error correction here that happens as well, and sort of a text to geographic resolution as well, but this is kind of a simple example of how this all works here. Okay. So I do want to talk briefly about evaluation. Oftentimes when you're building up some of these systems, you need sort of a way to evaluate how it's doing. One thing you could do as a simple check is take so first of all, you need sort of to build up an evaluation data set of natural language queries and valid query language queries. One simple thing you can do is sort of do a string match and see how close the generated query language is to the ground truth. But oftentimes it could be the case that different queries can get you the same result, right? There's n million possible ways you can arrive at the same result. It just depends on how you decide to formulate your query. So one thing you could do is if you do have a evaluation set, you could actually run it against your database and generate sort of tables and data frames. So for the text to CQL problem, I created maybe a data set of 40 different queries with human written CQL, and then we ran the pipeline against those same 40 queries. And once you have the results in table form, you can kind of just do a table to table comparison. So you can do sort of capture exact matches where the ground truth query generates the exact same results as the generated query. You can also give it partial credit. So if the generated query just only generates a subset or a superset of the ground truth table, that can be instructive. And then also you might have a no match where the query is just totally wrong and it doesn't match your gold standard results in TAN here. And then the other thing you want to capture are sort of the invalid queries. So queries that are not syntactically correct. They're using the wrong attributes or schema names. And that sort of, when the exception is thrown and is not eventually corrected by the system, typically you can capture that as an invalid query. So for text to SQL, as we were prototyping this, I ran this against a couple different models. I know it's pretty hard to see here, but on the far left, you have much smaller 7 billion parameter model. So this is Mixtral. So Mixtral 8x7b, a quantized version, Mistral 7b, Mistral Nemo, which is a 12 billion parameter model, Mixtral 8x22b, which is actually one of their top open source models, and then you have the frontier models Claude Haiku and Claude Sonnet 3.5. The green bars show sort of exact matches, and the purple is invalid SQL. And all the other colors are sort of partial credit. So the one thing we found when building these pipelines are that it's still the case that open source has not caught up to the proprietary frontier models. If you're putting this in production, you definitely want to go with one of the sort of proprietary models like Haiku and above. That's going to give you sort of the best bang for your buck. There are parts of the pipeline. So in this case, when you're like routing to the correct table or disaggregating the query, you can probably get by with a much smaller model to do this and save on costs, and it'll be faster as well. So those are some optimizations you can do sort of at the LLM level. Okay, great. So that's sort of the text to query sort of best practices work. The one thing I sort of want to finish off with is what do you do after you've constructed a pretty robust text to database pipeline? We have a number of NatSec customers interested in sort of taking this to the next level and sort of aggregating data from multiple different data sources, not just structured data, imagery, unstructured data, et cetera. And so here is an example of another use case we were currently in the process of building in production for a NatSec customer. The query this time is how many medical ships have we detected in the South China Sea in the past 24 hours with their transponders turned off. So this one is a way more complex query. It involves sort of making sure you can actually integrate images into your pipeline. There is some element of still hitting the database. You still need a valid text to query pipeline. And in formulating this problem, there are a number of different things we need to do to arrive at the final answer. So for this particular example, one, we need to correlate sort of AIS pings from the ships with image-based object detections. We need to also find instances of high confidence image detections that are programmatically generated with an object detection model that lack AIS broadcasts. And we might also want to look at trajectory data stored in a database and then structured data and find sort of discontinuous trajectories as well. So one thing you can do after you have successfully queried your database with text to query language is to give your pipeline a set of sort of additional functions. And even in this use case, we've introduced the use of Python REPL, which gives the LM sort of agency to run bespoke functions and tools in sort of a code editor to generate answers. We've also, in this particular use case, introduced statistics tools, correlation tools, and change detection. And we've given it to the model to actually use these tools as it sees fit once it's retrieved the data from the raw data from the database. And here's sort of a broader system design for what I'm calling text to answer. So this is, again, beyond text to query language. It really gets at the end user's intent of querying that data from the get-go. So there's a couple different pieces that you'll notice that we discussed earlier. This particular pipeline does have ontology resolution. So if you're thinking about a database or multiple databases with like vehicles or ships or aircraft, oftentimes there is some hierarchy that you need to resolve against. And we have that here as the first step. We also do have location resolution. And in this case, I don't think we use that RAG approach. We use like a more formidable managed service called AWS Location Services to resolve location text to spatial data. Once those two nodes are run deterministically, we do then run our text to database pipeline tool. So this is an RDS tool which had SQL, and we also had I think the AIS tracks in OpenSearch. Once those queries are run and retrieved, this is where the post-processing step happens, where we've given another LLM sort of agency to choose one of these higher order tools to post-process the raw data and give the results back to the analyst. So that's kind of the system design, or a sample system design for something that's a bit more involved there. So that concludes the talk. I did have a demo that I was going to try to run, but it's a bit risky at this point. So I'm going to leave it out. But the demo was basically flowing through this whole text to SQL workflow here. So it just shows you the flow of disaggregation, schema selection, subquery generation, which happens in parallel for all the subqueries, and then the final aggregation. But that's pretty much the talk. Happy to take questions now or stick around after if you have more specific ones. So, and again, Justin Jang at AWS, feel free to reach out for any questions. Thanks all.